All right. Let's go ahead and get started here.
Because like by not explaining what they are, it like shows that Aragon doesn't even know, or
Okay, let's go ahead and get started. Thank you. Okay. According to the questions on here, looks like we should run through these a little bit. I have decided that we will go ahead and do a quiz on Wednesday next week. So happy Thanksgiving. Thank you. That'll be good because then you won't have to worry about a quiz for after Thanksgiving. So you can get it done. And what? No homework. Well, I don't know about that. We'll see about that. So we will deal with those things, and that'll be a shorter day. So I'll make sure shorten it a little bit. Make sure it's something that we should be able to reasonably do in an hour's time. Now, section would be about sections 1, 2, and 3. Section 1 was about the quote unquote long way, the definition of the derivative, and that's what we're looking at here. You're probably going to have to do a couple of those. Involve some algebra, either the factoring and canceling, either the common denominator or the conjugate, which these were 2 of those. Then the second thing that would be on there, what we learned in this section was essentially the shortcut, at least for power rules. Now, one of the questions somebody asked on the whole question there was, were you supposed to use the shortcut or use the long way? On this assignment, mostly, except for the ones I gave you that weren't in the book, it was the shortcut. It was the power rule. So the vast majority of those, we were supposed to use the power rule. And we can look at a couple of those as well. Now, there'll be a few of those. Now, later on, we're going to learn a lot of other shortcuts as well for other functions. What's the derivative of sine of x? What's the derivative of e to the x? That kind of stuff. So we're going to have to learn a lot of different derivative rules. And what happens if you combine a polynomial with sine? What if you take x squared times sine x? What's the derivative of that? How do you do that? And so forth. So we got a lot of that to do, and that's what the rest later on in chapter 2 and into chapter 3 is about. So there'll be a little bit of that with these shortcuts on it. And then most of the quiz will be then what we're going to be starting today with the idea of limits. We had this rule about the difference quotient, the definition of the derivative here, and working it out, and it has a limit in it. What is a limit? How do we do limit problems? So we're going to spend a great deal of time over the next several days doing limits. Okay, I want to start by looking at a little video here on our home page here. I've got the class video, the lecture videos here, but I put a new link here. It says limit videos. All right, and this is a website, and it's got some pretty good ones here. CalculusHelp.com, and there's some other stuff on this website you might be interested in looking at. But the one I want to look at here real quick is this difference quotient, and then we're going to look at several of these here as well. And as over the next 2 or 3 days, you may want to come back to this site and look at these again just to help you with the concept of the limit. They're pretty short. They're not terribly boring to listen to, but so let's take a look at this one. This kind of reviews what we've done the last couple of days pretty quickly. There it is. Whoops.
Well, in calculus, the derivative is the slope of the tangent line to a graph. For instance, here's a graph, f of x, the point C that I've noted. The tangent to f at x equals c would look like this. In essence, a tangent line is just a line that touches the graph once at that point, sort of like a pencil resting there. Now, a function can have all sorts of different derivatives because, as you progress along a function, you can have all sorts of different tangent lines. Watch as the dot, which represents the x value, travels along the function, and how the tangent line changes as the dot moves. need to figure out a way to determine exactly what the slope of that tangent line is. And we do that using something called the difference quotient. In this section, I'm going to show you exactly where the difference quotient comes from. Here's a graph called f, with a point on it labeled x. My goal will be to find the slope of the tangent line to f at that point. First things first, the coordinates of this point are x, comma f of x. Now, here's how I get my formula. I'm going to move a small distance to the right of x, and I'm going to call this small distance delta x. It's mathematical language for the change in x. Therefore, this new location is a total distance of x plus delta x from the origin, and this new point has coordinates x plus delta x, comma, f of x plus delta x. Now, if I draw the line that connects these 2 points in red, it's called a secant line. It's not exactly like the tangent line we're looking for that I'm showing in blue, but at least it's a start. I'm going to go ahead and try to find the slope of this secant line. And to do that, I'll use the old formula from algebra, where slope is equal to y2 minus y1 divided by x2 minus x1. And I'll get the slope is f of x plus delta x minus f of x, all divided by the quantity x plus delta x minus x. And if I subtract those x's in the denominator, I get this. Now remember, this is the slope of the secant line, not the tangent line. So I'm not done yet. I need to find a line which is closer to the tangent line than this one. Let's look at that graph again. What happens if I were to make delta x smaller? In other words, my second point will be closer to x than it was before. Now, if I draw the secant line connecting my original point to my new point, which is slightly closer, I will get a secant line which looks more like the tangent line than the previous one did. It's getting closer to it. In fact, the smaller delta x is, the closer this secant line will be to the tangent line. Watch on this animation as the delta x goes from really big to really small. The red secant line comes closer and closer to the blue tangent line. We want delta x to be as small as possible. So therefore I need to make a small adjustment to my secant slope. Remember, that was f of x plus delta x minus f of x all over delta x. But we want to specifically say that that delta x needs to be as small as possible, so those lines basically overlap. And to do that, we'll use a limit. All we do is add in the limit as delta x goes to 0. In other words, I want delta x to become so small, it's almost 0. It can't be 0 because then I would have 0 in the denominator of the fraction. That's why I have to use a limit. And I say, get that delta x as small as possible. This is the difference quotient. It is the mathematical definition of the derivative.
Okay, so that's the same thing we had, except we used h instead of delta x, okay? So that is what we were using for what we ended up calling the long way of doing it, all right? So, first one we had on our homework was for 1 over x. And we know that now that we know the shortcut, we kind of know what we should end up with. Oops. Oops. All right. So we know that function 1 over x could be written as x to the negative 1. And so when we do our derivative, we should be ending up with something like negative 1 x to the negative 2, right? That would be our derivative right there. That's the shortcut, using the power rule. But to do it out by the definition, you're going to have to do both of those on the quiz. We're going to take, and we do our f of x plus h, so we put x plus h in for x, so we get this, minus f of x, so we get that. We need to bow tie, or we need to get a common denominator, so we multiply x by the top and bottom, multiply x plus h. So this fraction ends up with an x on top right here. This fraction ends up with an x plus h on top. We have our common denominator. Now I kind of skipped the next part, and this is the part you really got to be careful of. We got to do x subtract x plus h, which would be x subtract h. You subtract the x's, you end up with negative h on the top, and that's what I have right down here. So, what We get down to here. We've got negative x on top. We've got x times x plus h. Do not distribute that bottom. Leave it factored because some nice things will happen with some canceling generally. We got an h on the bottom, so we're going to multiply by the reciprocal. Again, good things happen. We can cancel those h's. So on top here, we just have -1. We have this. Of course, there's just 1 down here. Now we can let h go to 0, the part they were talking about. The whole, and the reason we're going to focus on limits now for a couple days is without the limit, we could not do calculus. Right? What does a limit do in this function, or in this thing we're doing? What does a limit do?
Allows it to get really, really close to 0 without becoming 0.
So the 2 points become 1, right? And we said that on day 1. Algebra 1 is slope between 2 points. What makes it calculus is we can do instantaneous rate of change. We can do slope at 1 point. And the only way to do slope at 1 point is let the 2 points get infinitely close together. So without the limit, we can't do it. We can't do the derivative. So limits are a big deal. And so we're going to investigate limits here for the next several days. All right? But right here, when the h approaches 0, we can go ahead and stick a 0 right in there for h now. So we get x times x, which is x squared. We get -1 over x squared, which we could bring that up on top if we wanted to. And of course, that's what we thought it should be because of our shortcut that we learned yesterday. Okay? The other algebra technique you're going to have to be able to do. Factor and cancel, I think we can all do that. But the common denominator and the conjugate are the ones we may need more practice on. So on this one, we got square root of x as our function. So f of x plus h, we get that. Minus f of x, we get that. All over h. The way to get rid of these radicals is to multiply over here by the conjugate. The conjugate means it's not opposite, but if you have a minus there, you change it to a plus. That's not opposite, it's conjugate. On the bottom, we don't distribute that through, just leave it alone. On the top, when you FOIL, this times this just gives you x plus h. The outers and the inners disappear. That's that a plus b, a minus b thing. The outers and inners drop out. And then the last times the last gives you -x. X plus h minus x, the x's drop out. You end up with just h on top. You got this mess on the bottom. We don't care how messy that is because we don't want to distribute it because the whole point here is to let the h's cancel. And so the h's can now cancel and we end up with 1 over this. Now we can come in and let the 0 go in for h, right? Because we divided out the part that was causing us a problem. Before, we would get 0 over 0 if we tried to put a 0 in for h. Now we've canceled the h's. We put a 0 in for h down here. We end up with square root of x plus square root of x. That's 2 square root of x. Now, using our shortcut, square root of x we know is x to the 1/2. The shortcut said bring the 1/2 down in front and subtract 1 from the power. So we end up with that. Are these two things the same right here? Are they the same thing? They are. Negative power means drop it down to the bottom with the 2. Make it a positive power. X to the 1/2 is square root. Those are the same thing. The shortcut and the long way of doing it both give us the same thing. But it's important to understand the long way, the definition way, because that's where it comes from. That's what slope means. That's what derivative means. All right. Let's take a look at a couple of problems some people ask about in the book. And let's see if we can make this. I'll go ahead and try this here today, see how this works. A few people ask about number 36. Is that working? Yep, seems to be. Okay. Let me know if that doesn't seem to quite work right. Was 36 one we had? 36? Is that one of the homework problems?
Yes.
Okay, I thought it looked like some people asked about that one. So we have 3 over x plus 1 to the 2nd power We're not supposed to do these by the definition, the ones in the book where it says find a formula for f prime. We're supposed to use our shortcut, our power rule. Now, our power rule doesn't work, though, when it's written like this. What do we have to do? We have to rewrite it so that this is x plus 1 to the negative 2. Now, I haven't done any calculus to that. That's just algebra rewriting. All right? So I'm going to still label that as f. Now, I'm going to call that, now I'm going to do the derivative, use my power rule. Now I've got f prime. The 3 just stays there. The negative 2 comes down in front, giving you negative 6. What about the x plus 1? Stays the same because that's a left shift. The slopes will also shift to the left. And the power? Negative 3. It is perfectly fine to leave your answer like that. You do not need to then go back to a positive power. That's fine. I don't care about that. All right, while we're on that topic, let's move on to 45 and 46. On 45 and 46, again, we have to rewrite. On 45, all we need to do is FOIL that out. So on 45, we're going to take and get f of x is 3x squared. What do we get? Plus 2x minus 8. Is that right? So we FOIL it out first. And so the derivative, now we can do the power rule. And we get what for the first one? 6x to the first. What's a derivative of 2x? 2. Now, you're going to get to the point where you don't even have to think of the power rule on that one. I mean, 2x is a line. Its slope is always 2. So the derivative has to be 2. You can think of it as, okay, there's a 1 there. Bring the 1 down in front. 1 times 2 is 2. X to the 0. X to the 0 is 1. So you have 2 times 1. But you really don't even need to think power rule in that. 2x is a line. Slope of 2. The derivative is 2. What's the slope of negative 8? 0. A constant is a horizontal line. Has a slope of 0. So it just disappears. And there is your final answer. Okay? Let's take a look at 46. 46 says the square root of x, subtract 3, all over x. Okay? That's f of x. What do we need to do with that? Bring the x up top. Most people, it seems like every year, that's the algebra thing you remember the most, and that's perfectly fine. Now, this is not calculus I'm doing at this point, it's simply algebra. So I'm going to make this x to the 1/2 minus 3, and then I'm going to bring up an x to the negative 1. Then you distribute those, and you add the powers. So this would be x to the negative 1/2 minus 3x to the negative 1. Okay? So again, I still haven't done a derivative yet. Now, I am going to make a comment, though, here. Because of something we'll do later on, as the year goes on, I think most people will not bring this up like that, but will instead think of splitting the fraction up. Think of making this x to the 1/2 over x minus 3 over x. Because of a thing that we do later on, it actually makes it easier to think of it this way rather than the other way. Here you subtract the power. Well, if you take 1/2 minus 1, you get x to the negative 1/2. Here you got 3 over x. You just bring the x up, and you have 3x to the negative 1. Either way, you get to the same place. Then your final answer for f prime, bring the power down in front, negative 1/2, x to the negative 3/2. We subtract 1. Negative 1/2 minus 2/2. That'd be negative 3/2. Bring the negative 1 down in front. That would become a plus 3x to the negative 2. Now, I know in Algebra 2 class, and when I taught algebra, I had the same rule. If your problem started as a radical problem, then you would want radicals in your answer. That's not a big deal for us. For us, we'll get to this point, we'll just leave it like that, and that's fine. All right? If we need to change it to a radical or something like that, we will. For example, you can probably tell where we're going to go with this. Combine what we learned in chapter 1. Where we'll end up going with this is I'll give you this function f, and I'll say find the stationary points. Well, where are the stationary points? Where the derivative is 0. So you'll go through this process and find f prime, and then you'll set it equal to 0, and then you'll have to solve that. Well, to solve that, might be in your best interest maybe to change it into radicals. Or maybe not, or change it into a fraction. So we'll determine what algebra we need to use in a particular problem. But we're not going to make a big deal about just rewriting things just to be rewriting. Okay, we'll rewrite them if it helps us, and we'll expect everybody to be able to do that rewriting that you learned in algebra. But for us right now, we don't care about that. We're just trying to get the derivative. All right? So we stop there. Somebody mentioned 30. Now, a few people mentioned 39. 39 is simply that tangent line stuff. 39 is y equals m times x minus x1 plus y1. So you need the slope and you need the point. Well, they told you in the directions that the slope was 4. And they wanted you to go back on example 5 and find the point. All you had to do was go back on example 5 and find f of 1. So you go back one page and you look on the graph at 1, and what y value do you get? Anybody? 5. You just look at the graph of f, you go to 1, it looks like it's about 5. Okay, so you got y equals 4, x minus 1, plus 5. Write the equation of tangent line. That's all that was doing. Really, to be honest, I just wanted some more practice of writing the equation of tangent line. The problem's it gets more interesting if we'd have went on and done 40, 41, 42, and 43, because what they did is they took that f graph and they shifted it up, they shifted it right, they stretched it, and then that affected then your points, okay, and where the slope was and so forth. So that's kind of was the idea there. But I didn't care so much about that. I just wanted to get some practice with the equation of tangent line. Okay? All right, get your calculators out and get on the scratch pad to the calculator screen for a second. Okay? Go on the calculator screen. Now, this is always kind of fun to see here. Uh-oh. If anybody wants to know how to clear the scratch pad, you go up, you go up, click on that thing, a little triangle right here, and it says clear scratch pad. Okay? If you want to get rid of that stuff. If you have some stuff on it. All right, what I want to show you today is how we can use our calculators to do these derivatives, these shortcuts for us. Now, to be honest, we don't use that very often. Where you use it the most is when you have to, if you're working on your homework and you want to check to see if you got the right answer. You can use your calculator as kind of electronic solutions manual. Okay? This is why these calculators say CAS on them. CAS stands for Computer Algebra System. It will do the algebraic type things for you. So let's do one. If you go under Menu to Calculus, go to the first choice, which is Derivative. Okay? And this thing pops up. Okay? Now, let me make a couple comments about that notation, first of all. The notation we've been using up till this point has been just function notation. So if I want to do the derivative of f, I write f prime of x. Okay? But sometimes we won't call the functions f or g or whatever. We might use y equals. So the derivative would be y prime. Okay? Not a big deal. But there is also this notation. It's called Leibniz notation, named for one of the guys who's credited with kind of developing calculus. Isaac Newton and Leibniz were the two guys. And the notation is this right here, dy dx. Okay, dy dx. Now where that comes from is slope. Change in y and change in y over change in x. Okay? So delta y over delta x, we write dy dx. That also means derivative. Think of it this way. Think of the d meaning derivative, and think of the derivative of y with respect to x. The derivative of y with respect to x. That's telling you what the input variable is. The input variable is x. Now, why do we need extra notation? Well, actually, this notation could come in really handy. For example, yesterday, I was telling you, I wrote a whole bunch of these on the board. F of x equals x squared. F prime of x equals what? 2x. Well, if I would have used Leibniz notation instead, I could have saved myself a lot of writing. Okay? Because one of the ways we could write dy dx is we could write this. And you often see this. Matter of fact, that's the notation you're seeing right here on your calculator. Is we can do that. I mean, that's the same as dy dx. Think about in algebra. You have 1/3 x. You put the x out in front. It's the same as if you had x on top, x over 3. Well, that's kind of the same thing here. This means a derivative of y with respect to x. Well, what I could have done instead of this is I could have said the derivative of x squared equals 2x. And I could have written all that on one line instead of having two separate equations. That says the same thing. That says the derivative of x squared with respect to x is 2x. Okay, so that's notation we want to get used to seeing. Another thing that we sometimes have, instead of y double prime or f double prime, we can do this. The second derivative is simply the derivative of the first derivative. Here's how, with Leibniz notation, I would write the derivative of the derivative. Well, if you look at that, that kind of looks like d squared y over dx squared. Now, this is in your book at the beginning of section 2.2. And you might remember this from that matching activity we did with the second derivative. Those cards had this notation on it. I don't even know if you noticed it or not. But that notation was on there. Okay, we hadn't talked about it yet, so I just kind of didn't say anything. Hoped it wouldn't confuse you. Okay? Now, people do get confused when they see this notation on questions because they think they're supposed to be squaring something or something. That's not what this means. It does not mean to square something. Okay? It just means second derivative. Okay? So when you see that, it just means second derivative. All right. So that's the deal with notation. So now let's get back to the calculator. So let's say we wanted to do the derivative of x squared on our calculator. I just go into this box right here, and I hit an x. And I come up into this box, and I type in, let's do an x squared. And I hit enter, and it'll do the derivative. Okay? It's kind of nice. There's another place to get it. Over next to the 9, there's this template thing. And if you hit the template key next to the 9, you can see the derivative notation is right over here, if you don't want to go into the menu. Notice right next to it is the second derivative notation as well. Okay? And then one down here has got an n in it. You can have as many derivatives as you want. Okay, third derivative, fourth derivative, whatever. We don't use those that often. Okay? Let's have it do the derivative of number 46 here. Let's type that in. Okay, so I've got a fraction. Got a square root. Make sure you put your -3 outside of the square root, not inside. That's what I got. Is that what we got? It is?
Yes.
How do you know?
calculator too, right?
No, I'm sorry, I meant on our homework. Is that what we got? Still up here on the board, right? We have this. Now, what I had told you was, you want to use this as kind of electronic solutions man. You're working at home, you did your derivative, now you want to see if you did it right, so you type in your calculator and you do it. Because there will never be a quiz question on the AP test or any of our quizzes where I ask you to do a derivative and you're using your calculator. Those will all be no calculator. Okay? Because I'm not interested in quizzing you on how well you can push the buttons on your calculator, right? So, but it can be useful to check your answers. But many times as we get into, not even real difficult ones, just pretty basic ones, your calculator is not going to simplify it the same way you did. Okay? There's a couple ways you can do this. One way is to go ahead and tell the calculator, if you go under Menu, under Algebra, to expand. If you tell the calculator to expand, and then up arrow so you can capture that answer you just had, hit enter again. Now it gives you that. Okay? Now, it's a little closer, but I'm still not sure I can very easily tell. Let's see, here's 3. This one would be 3 over x squared, so that's this first one. And this is 1 over 2x to the 3 halves. This would be 1 over 2x to the 3 halves, and it's negative. Yeah, it looks pretty good. But, it doesn't look exactly the same. So let me show you something else you could do. And this is probably what I would choose to do. I would just go ahead and type in what I got. I'm just going to go 1 divided by 2. Whoops, that was negative. I would put negative 1/2. Okay? Times x raised to the negative 3 halves. Okay? Plus 3x to the negative 2. Okay? Now, when you do that and hit enter, okay, see what it gave me? And now I can see that those two are the same. Now let's pretend we hadn't done this yet. Right? Let's pretend I hadn't done that expand thing. So I had the calculator do it. I typed in what I got, and I want to know if those two are the same. Probably the slickest way to do it is do this. Take the calculator's answer. Okay, I'm going to grab the calculator answer, hit enter. Then I'm going to hit the equal sign. And then I'm going to go up and grab what I had typed in, and I probably would have just done this first. I would have grabbed the calculator's answer, hit equals, and then typed in what I had done, and hit enter. And if it says true, then you know you got it. If it says false, you know they're not the same. Okay? So, that's a pretty good way to tell. Use the equals. All right. Any questions? Any other questions about that? I have to get a new seating arrangement for the back corner. I have to move some people around. I have to move some people around.
Clark.
All right.
Clark.
What?
Mrs. Larson's at the door.
Oh, Mrs. Larson.
Oh, wait, Mrs. Larson.
That's strange.
All right. Okay. You're going to want to put this in your notes now. Let's move on to the idea of limits. So as you're doing that, I'll just summarize here. We've got essentially two things that we have learned up to this point that will be important for the quiz. One is the definition of the derivative, working them out the long way, and all the algebra that goes with that. And that'll be no calculator for the most part. I'll show you on Monday, I'm going to show you what we can do with the calculator on limits. Now, again, the calculator does so much. We can just type in a limit and it'll just tell us the answer. But I'm not interested in that we can do that. There's a way, there's something else you're going to do on the calculator to show that you understand the concept of limit. Okay, so there's the definition of the derivative, which is kind of that long way, and then there's the shortcuts. And you have to do a few of those. I mean, those are the two main things that we've learned up to this point. All right, so the next thing we want to talk about is this idea of limit. Okay, so, and this is unrelated now at this point to derivative. All right, it's kind of like the square and rectangle analogy I've used for some other things. A square is always a rectangle, but a rectangle is not always a square. A derivative, by definition, is a limit. A derivative is 2 points getting closer and closer and closer together. So a derivative, by definition, is a limit. But not all limits have anything to do with derivatives. You can learn about limits starting in Algebra 2. And you may have talked about them in advanced math. So if I give you this problem right here, limit as x approaches 2 of x squared plus 3, does anybody have a guess of what they would write down for the answer to that? 7. And you got that by doing what? Direct substitution, plugging in a 2, and you would be exactly right. Now, that doesn't really tell us much about what limit means. Limit does not mean just plug in a 2. Okay, as we saw in our derivative examples, as h approached 0, we couldn't just plug in a 0, because what happened? 0 divided by 0. But if we kept going and got some algebra happening in there, eventually we could plug in a 0, right? So in a limit problem, the first thing you always want to try is direct substitution. See if you can get an answer. And that's what happens on this one. But let's understand what we're really talking about there. X squared plus 3 is a parabola shifted 3 up. We're talking about as x approaches 2. Well, yeah, on a parabola, on this parabola, at 2, there's a 0.7. But that doesn't, the limit doesn't mean just what do you get at 2. What a limit means is as x is approaching 2. As the inputs, and I'm talking about for both sides now, as the inputs are getting close to 2, what are the outputs getting close to? Well, they're getting close to 7, right? So if I put in 1.999 or I put in 2.001 into this thing here, I would be getting numbers getting really close to 7. So we say the limit is 7. So that's the simplest example you can have of a limit. Direct substitution. All right. Then what happens if you get one like this? Limit as x approaches 3, x squared minus 9 over x minus 3. Now, you try direct substitution, and what happens? You get 0 divided by 0, which is undefined. Now, what you'll come to learn today is that when you get 0 over 0, what that is code for keep going. Something is going to happen, probably not. You'll be able to get an answer for a limit. Possibly. You may not, but you won't know until you keep going. All right, now what's the obvious thing to do here? Factor out. So you make this x plus 3, x minus 3, over x minus 3. You can cancel the x minus 3, and just like the h's, that's the bad stuff that we just canceled out. That's the part that was making us have 0 divided by 0. Now what we have is x plus 3. Now let's talk about this just for a second. When you were in algebra class and you did a problem like this and you factored it, you know, you would say, oh, okay, this is equal to this. The thing we started with is the same as this. Well, we talked about this earlier in domain and range. They're not really the same, are they? What's different? What's different about this compared to this? You can't put a 3 in this, right? You put a 3 in this, it's undefined. Can you put a 3 in this? Absolutely. But other than that, they're exactly the same. So if you were to graph x plus 3, that's a line, right? Y-intercept of 3. This would also be a line with a y-intercept of 3, except for what? Right here, there's a hole. Probably don't have to make it that big. There's a hole at 3, right? What's the y value where that hole is? No, well, but I mean, what's the y value where the hole is? 3 plus 3 is 6. So you can't plug a 3 into this, but if you do the factoring thing, and then, just like we did with our h, once you get down to here, now we can go ahead and plug the 3 in, and we get 6, and that is our limit. Because again, a limit doesn't care if the point is there or not. The limit says, and I said this earlier, say it again, as x gets close to 3, what do these y values get close to? They get close to 6. And so we say our limit is 6. And we're going to watch a short little video here that says it in much the same way, but I think it'll help reinforce it, and plus it's another place you can go to if you want to look at it. So that is, there's still a limit there. So, normal graph, everything seems obvious, limit, easy. Here you try to plug in 0 over 0, keep going, do some algebra, maybe conjugate method, maybe common denominator or factoring. You can still get a limit. The third possibility is this. Let's do this one. Limit as x approaches 1. X squared minus 7x plus 6 all over wait, that's bad. No, I gotta change that. I gotta change that.
What order? You got it. You okay up there?
I think so. Okay, I think that's what I want, right there. I think. I hope. This will be embarrassing. Okay? All right. So we get one like this. And we go ahead and we do what first? Direct substitution. So go ahead and put a 1 in there. What do you get? No, but I mean, specifically, what do you get? What over 0? 8 over 0. Okay? So you get 8 over 0. Now that's undefined. Okay? Well, this also was undefined, but they're very different. 0 over 0 means something much different than 8 over 0, or 2 over 0, or negative 6 over 0. They mean very different things. 0 over 0 is going to mean a hole in the graph. A hole in the graph, as we saw here, means the limit is still going to be there. Because a hole in the graph typically means that the y values meet, as you're going to see here in a little bit on this video. But 8 over 0 means something else. 8 over 0 means infinity. 8 over 0 means vertical asymptote, or 2 over 0 or something like that. Okay? That means something very different. So Now you have to keep going as well, but probably what's going to happen is your answer here is going to be does not exist. All right? But we're going to watch the video first before we go on, because we'll have to do more than just say does not exist for our answer. We'll have to tell why it does not exist. Okay? And we're going to watch on the video and hear more about that and what that looks like. Okay, so let's do that. And again, these videos, right down here where it says on the class website where it says limits videos, that's how you get to this. Okay? All right. Let's start. Uh-oh.
Now we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot, so we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height. Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4.
It's really important, that idea of getting close to, right? I mean, even though we plug a 2 in and we get that output, again, what we're saying is as x gets close to 2, the output's getting closer.
There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of negative 2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to -2. This begs the question, when exactly does the limit exist? We examine that in the next module.
Okay, so we had talked over here about one that does not exist. We don't say limits are undefined. Functions are undefined. Limits either exist or do not exist. Okay?
Now you have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet
This is a
for
good way
dinner,
to think
and you're
about it.
meeting at a
This
diner
example.
that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x, as long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists.
From both sides, that's the key. We have to look
Now
at
it's time to get
both
down to the
sides.
brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol.
That's what we're going to use on the third one.
Our height that we arrive at from the left is called the left-hand limit of f of x as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal.
Okay, that's what we're saying. The cars have to meet for the limit to exist, which means the limit from the right has to be the same as the limit from the left. Okay, that's what we're going to look at over here. This limit does not exist. There's a vertical asymptote there. We're going to have to say, hey, what's happening on the left and what's happening on the right? Because if the limit doesn't exist, that means the cars aren't meeting. So we got to see where are the cars then? Okay, where are they at?
Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
Now there's two different ways, two basic ways that the limit won't exist, the cars won't meet. One is the example they gave, okay, where there's a break in the graph. Now, if you have a graph on your book, some of your book homework, you'll have that. They'll give you a graph and it's got all kinds of breaks and jumps in it. What's an equation going to look like that's got breaks like that? It's going to be a piecewise, right? So it's going to be easy to identify. If you have a piecewise function, then you're right away you should be thinking, hey, there might be some breaks here. Now there might not be. You know, one graph might go here, and then the next one will take off right from that same place, and the next one will take off from that place, and there might not be any breaks. But you might have breaks too. This piece will go here, the next piece will start somewhere else, so you might have a break. So anytime you see a piecewise function when you're doing limits, you kind of think, hey, you know, let's make sure that something strange isn't happening there. Maybe there's a break. Okay, the other way you can have a break in a graph is a vertical asymptote. Okay, and that's this last one we're going to look at here real quick, and then we'll finish up this problem, number 3 on the board.
In this section, we'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you plug in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote. And this holds true for this function. Let's take a look at the graph of f at x equals 3. Well, remember, an asymptote is a line which a function cannot reach. Here we have an asymptote at x equals 3, because when we plugged 3 into f, we got a constant divided by 0. Now, by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of f of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say that the limit as x approaches 3 from the left of f of x is negative infinity. Vertical asymptotes aren't the only asymptotes which relate to infinity. Horizontal asymptotes.
All right. So, we're going to focus on working on limit problems here. That the ones in the book, a lot of the ones in the book are going to be graphical. Okay, so you got a graph with a break in it or a hole in it or something like that, and they're going to ask you about limits. And they're going to ask you about the regular limit, like as x approaches 2, x approaches 3, x approaches 1. But by regular limit, you got to look on both sides. Okay? They'll also ask you about some one-sided limits. What's the limit from the left? What's the limit coming from the right? Okay, we're going to do a worksheet with some that you work out algebraically, not graphically, because there's going to be no calculator. All right, these will be on the no calculator part of the quiz. Now, one of these 3 things is going to happen. Okay, the first thing that could happen is direct substitution works. You always try that first. If you do direct substitution and you get a number answer, that's almost always it. You're done. Okay, I can't think of a situation with just a basic equation where you plug in a number, get a number out, and that's not your answer. Okay, now if you have a piecewise function stuff, that's a different deal. Okay, for example, but these are going to be easy to see because number one, it's going to be a piecewise function or it's going to be a weird graph or something like this. What if I had a graph that did this? Okay, and this point right here was a 2. Okay, and this was, let's say this was 1 right here. So, and that's the function f, let's say. Oops. People might be watching at home. There we go. All right. So, this is a function f. What is f of 1 for that function? 3. You plug in a 1. Now, we don't have an equation to plug into, but you plug a 1 into that graph, you get out a 3. What is the limit as x approaches 1? 2. Right? Where are the cars meeting? The cars meet at 2. The diner burned down and moved to they build a new one in a new spot. Right? That's what that would mean. But the cars are driving along the road and they're meeting at 2. That's the limit. Even though there's a hole there, Don't let that bother you. It doesn't matter with the limit. The limit is 2, but the output is 3, so they can be different. All right, but most of the time for basic functions, basic equations, you plug in, get a number, that's your answer. The second thing that will happen is you get 0 over 0. Now that's what happens most of the time in the limit problems we do. We get 0 over 0. What you have to do at that point is one of the 3 algebra techniques then that we've been talking about. You're going to have to do factoring and canceling. You might have to multiply by a conjugate, or you might have to get common denominators. All right? So not only in the definition, the limit definition of derivative will you have to do that algebra, but in some limit problems like this, you have to do that algebra. So the algebra will be a big part of the quiz. Okay? And then once you do that, something nice will cancel out, and you'll be able to get your answer. All right, the third thing that could possibly happen is this one. You get a vertical asymptote, 8 over 0, something like that. So you know that something weird is happening from the left and the right. Now, if we had a picture of this, a graph, we could tell. But this is going to be no calculator. So you're not going to have a picture of this. All right, so you have to do it numerically. So here's what you would write on your paper. So you would say, okay, the limit does not exist. We're getting a vertical asymptote. So I have to look at x from the left. Now that's that little negative sign that they were writing on there. That means from the left, the little negative sign. Okay? And we'll just call this function f. And we're going to investigate that. Okay? Now, I guess I could have factored this. Even though we were getting 8 over 0, I probably could have looked at this to see if it factored. The top is what? X plus 3 and x plus 1. And the bottom is x plus 1, x minus 1. Right? The x plus 1s do cancel. Unfortunately, that's not what was causing me to get 0 over 0, because I'm plugging in a 1. Right? So when I put a 1 into this, so this simplifies to x plus 3 over x minus 1. So for my purposes here, I could go ahead and do that. It might make my substitution a little easier here. Okay? So I'm going to go ahead and do that. Now, of course, if I put a 1 in, I get 4 over 0. Well, it doesn't matter if you get 8 over 0 or 4 over 0, whatever. It still means vertical asymptote. So I'm going to look at x as x gets close to 1 from the left. I don't have a graph to look at, so what number would be getting close to 1 from the left? Point 9999, right? Something close to 1 from the left. So 0.99999, whatever. So I'm going to think about x being 0.999. Now I'm going to go ahead and substitute that into my x plus 3 and my x minus 1. So what's 0.999 plus 3? 3.999. Now, in other words, getting close to 4 is really all we care about. But it's not the top that's the key. It's the bottom. What's 0.9999 minus 1? Negative 0.0001. Now, I don't even care what it is exactly. But the key is it's a negative, really little number. And the closer I get to 1 from the left, the littler it gets, but it's always going to be negative, right? Because I'm on the left of 1, so I'm a little smaller than 1. Now, what's 3.999 divided by a really little negative? Yeah, I don't even care that it's 3.999. I just care that it's some positive number. Take some positive number divided by a really little negative, and you get a really big negative. Negative infinity. Negative infinity. Okay? You wouldn't even have to write out these numbers. If you wanted to, just write, okay, if I put in a 0.9999, I get a positive on top and a small negative on the bottom. That's the key. I'm taking a positive number, about 4, and I'm dividing it by negative 1/1,000,000. Well, that's negative 4 million. Right? Anytime you divide by something really small, it gives you something really big. All right, so that tells me on the left, it's going to negative infinity. And then I repeat that on the right. As x approaches 1 from the right, I put the plus sign there of f. So what's a number to the right? 1.0001. So a number just a little bigger than 1. Well, 1.00001 plus 3 is like 4.0001. You know, I don't care about 4. And 1.00001 minus 1 is a positive real small number. So now I have a positive divided by a real small positive gives me a real big positive. Positive infinity. Okay? Didn't show. Okay? Positive infinity. So anytime we answer a limit question with does not exist, we have to say why it doesn't exist. And think about the video. The only reason a limit doesn't exist is if the cars don't meet. So if the cars aren't meeting, we got to say why aren't they meeting? Where's the one from the left going, and where's the one from the right going that they're not meeting? So that's what I do. Now we can tell then what a graph of this would be. At 1, we've got a vertical asymptote. And from the left of 1, it's going to negative infinity. And on the right of 1, it's going to positive infinity. I don't know what the rest of the graph is doing, but I know at 1, it's doing that. And this car is going to go up like that, and this car is going to go down like that, and they're not going to meet. And so the limit does not exist, and this tells why it doesn't exist. Okay, so those are your options. Simple substitution, you get an answer, that's your limit. 0 over 0, do some algebra, then do your substitution, get your limit. Sometimes you'll substitute, you'll get 0 over 0, you'll do some algebra, you'll substitute in, and instead of getting a number, then you'll get 8 over 0. And then you'll say does not exist, and you'll have to tell why it does not exist. Okay, anytime the limit doesn't exist, we have to say, we have to look at the left and the right. They call them the one-sided limits. Okay, if it doesn't exist, that means the cars didn't meet, so you have to tell us where did the left car go, where did the right car go. All right? That's it. So, your homework, 2 parts. On section, get out your assignment sheet for 2.3. We didn't quite cover all of section 2.3 here, so we're only going to do the 2.3 line up through number 26. Yes?
Can I have one of those sheets?
You may. 2.3. Up through number 26. And then this worksheet here on limits. These are, they're algebraic limits, it says. What that means is no calculator. And this worksheet is where you're going to be doing the conjugate method, the common denominator method, the factoring method. That's the practice on the algebra here, is on this worksheet. I think the ones in the book are a little more conceptual, a little more about graphs. Of course, that's going to be part of the quiz as well. Okay? All right, so we've shifted gears a little bit. We were focused on derivatives and the definition of the derivative and all that. And now we've taken a little side trip to just investigate limits. Because it's such a big, important part of the definition of a derivative, we're just going to investigate limits for a number of days here. Okay? And that's what this is about. Okay. Go ahead and go to work.